let's see here. So what I wanted to do today was we had a John Key and Alexi Raga released or started doing a blog post series on the stuff they've been doing with Haskell Works, and I thought it would be kind of neat to just go through like how succinct data structures work and some of the cool things you can do with them a bit. Maybe to feed into the stuff that they're doing and partially because I think there's some neat stuff that hasn't been built in this space, and maybe we could try and build some of it. That way it's more live coding rather than just class. So at least that's the thought. So how many people here actually know what a succinct data structure is? And how many people don't? I should probably set up a straw poll. Wow, my screen is really bouncy today. I apologize. Over to the results here and see. So if you follow the link, you'll be able to vote. Let me throw this into my split coding and review. All right, so there's absolutely nobody here so far who seems to know what the hell I'm rambling on about. So we've got something that seems to be fresh for the vast majority of the audience. Got a pen. This will probably require me to actually sketch a fair bit. State. And drum roll, please. I should be able to. All right, so maybe 20% of the audience being super duper favorable to me have encountered this before at a very minor level. So let's see if I can get the viewing angle on this thing right. If I do that. Aha. Okay, so what is a succinct data structure? What I'll do is I'll sketch out the idea of what you can do with a succinct indexed dictionary, and we'll go from there. So let's say, this is going to be a little bit weird. I've done this in person a lot, and there's been a couple of streams I've done before, but none of them have been recorded with decent quality, which is one of the reasons why I wanted to go with this now. So let's say you have just any bit vector with a bunch of zeros and ones in it. Okay, so you have n bits, k of them are ones. If you knew n and k, then I'm going to try and see if I can zoom out a little bit here. That way, maybe the focus problem would be a little less bad. If I knew n and k in advance, then what I could do is I could say, well, then there are n choose k such possible bit vectors. Basically, I have n bits, k of them are 1. There's k, like n choose k different places I could put those ones. And so if I were to write down which of those n choose k possibilities I would have, then to represent this bit vector, what I would do is it would take me, I could just write down which of the log base 2 of these n choose k possibilities I have. And so this is the amount of information here. This is the amount of entropy. And it is 0th order, which means that I'm not giving you any extra information about like what are the odds of a 1 following a 0 or a 0 following a 1, etc. And it's empirical, which means that I don't have any a priori model. So if I wanted to store this bit vector in the smallest possible space, then what I could do is just represent the amount of information. Yes, the ceiling should be around the log. Sorry about that. And yes, I apologize for the fact that the paper cam keeps refocusing. I keep meaning to replace it. It's on a goofy little arm over here that is unfortunately a little too close to where I have to put my hand. Maybe I can pull it way up, but then if I do that, then it's going to have a very large field of view. Maybe I can clip its field of view. Drawing camera property filter. No, not filters. Properties. Configure video. No. I have to figure out how to clip this stupid thing. Drawing cam. Properties. Can't remember how to transform this thing. Edit the transform on it. Yeah, this is going to be too hard. I'm not going to get it done right now. So I'm just going to zoom in and apologize for the fact that the paper cam keeps zooming in and out. Okay. So if I just wanted to write down this bit vector, then what I could do is I could just write down which of the n choose k possibilities. If I needed if it didn't take this much space, there would be some bit vectors I couldn't represent. And this is great as long as k is really small or k is really large. If k is right at the middle, then this is kind of bad. It's n choose k. We have k ones, and we can put them anywhere we want. We're choosing k of them. We're choosing k of n things. Okay, so the problem is if I were to switch into storing it in this much space, then I would lose the O1 access to S sub I. Yeah. So let's just call this like access S at position I is, just give me the value of S at position I. And right now, that's O1. But if I switch into this encoding, I probably have to decode it most of the way and then fight with it in order to get access. So what I want to do is I want to get down almost to this space and still have efficient access. And maybe I should zoom in a little bit more because this is going to be kind of horrible. I apologize if that's not readable. And if I'm going to ask... if I'm going to ask for this kind of time bound and almost this space bound, I'm going to ask for a few more things as I go. So Midsaitsuki, what we're doing right now is we're starting to build up the idea of what's called a succinct data structure, which is data structures that are as compressed as possible, plus a very, very small extra term, and which can still be used like as efficiently as they could before. That's the general idea of a succinct data structure. So in order to, so I can't really hit this space bound. Hitting this space bound exactly would be kind of magic. But there's three different terms of art that get used in this space. One is the idea of an implicit data structure. So I'll say an implicit data structure is one that is H0 star plus big O of 1. And this means that you just have a constant amount of overhead. On the other hand, it will say that a succinct data structure is going to be h0 star plus little o of h0 star. Now, little o notation is not very common. Like you've probably encountered big O, big theta, omega. Little o basically says no matter what constant you pick, I'll beat it. This is strictly better than. Is the like if you view big O as less than or equal, you can view a little o as an actual strict less than. And then we can say compact is big O of h0 star. So these three terms of art get used in this succinct data structure space quite a bit. You'll find a few other references to the idea of something being succinct, and they don't really take on this connotation. But this is the, like in the compressed data structures world, this is what succinct means. So what is this saying? This is saying that it takes optimal space plus a term that is, as the size of my structure goes to infinity, the overhead is proportionally going to nothing. So as I get bigger and bigger, this thing has less and less overhead. Whereas n log n or something like that, as I get bigger and bigger, the overhead's still growing, but it's growing relatively slow. So this is a rather desirable space bound. And what I'm going to do here is I'm going to make a bunch of claims about this, and we can play with actually building a couple of designs that would implement this if we really, really want to. But I actually find it's much more useful to sort of take these things as given and then build on top of them. Because building one of them isn't terribly informative. I mean, it's a lot of work, and I built a little succinct library for doing this, and then John Key and Alexi Raga went and built all of it as Haskell works, and have, I believe, pushed it all out to Hackage and whatnot. So there's a whole bunch of stuff already implemented in this space. And so what I want to do is I want to say, once we have this sort of weird alien data structure, which is actually quite difficult to build, what can we build out of it? So having this ability, so what I want is this ability to access my data structure in O1 time. But if I'm going to ask for a pony, I'm going to ask for a really, like a tricked out pony. So what I want to be able to do is ask for the rank, which is, this is going to be the number of occurrences of the symbol alpha in my string. And for my purposes, I'm going to choose to have everything be 1 based. So we're going to pretend we're in Fortran. And we're going to start numbering at 1. And these are difficult because algorithms. They're actually rather non-trivial papers to implement. It's actually pretty easy to build a nice compact data structure for this, and the compact one is actually pretty damn efficient when k is roughly n divided by 2, and we're going to see a bunch of use cases where that is the case we encounter, and so we'll often just use the compact thing, but we're going to use this vocabulary from this notion of what's called a succinct indexed dictionary. And this is a Googleable term, which will get you to the Wikipedia page, which will get you to the Roman, and Rayo, and a couple of other variations on the theme. Okay, so what I want is I want this access to the ability to compute rank. And what this is going to be, this is like a prefix sum. Rank of 1s is going to be the number of 1s up to a given position. So if I ask for rank of 1s up to position 5 here, it'll tell me 3. There are 3 1s in the first 5 characters. And then I'm also going to, like, since we're continuing to ask for ponies, I'm going to ask for the ability to select alpha SI, which would be the position of the ith alpha in my string. And I can also do this in O1. There are data structures for all of these. And if you can compute rank, you can get access. Why? Because, like, access here Si is just like the rank of ones in S up to position I minus the rank of ones in S up to position I minus 1. So if you can compute rank, you can compute access. So we can get it for free. And if you can compute rank, you can like binary search for select. But that's going to cost you a log to do like a big open binary search to find the position. Okay, so this is the data structure I'm going to assume. And let's see what we can do with it and what are some interesting properties of these rank and select operations and whatnot. Because I think those are the things that are informative, that kind of take you outside of the usual, hey, search is a log, build a binary tree, waste memory, usual computer science stuff. So let's build some interesting things on top of this. All right. So we're going to assume this data structure. We'll pull it out of the literature as needed. I'm going to set this piece of paper aside, and we'll go from there. So what we can say is we can say some things about rank and select. So rank, alpha Si is I minus rank of the complemented version of alpha Si. So what did we say here? We said before that rank was the ability to count the number of occurrences of a given symbol. Well, if we're asking for the rank of zeros, this is just I, like if there's I symbols and they're all zeros or ones. If it's not ones, it's zeros, and vice versa. So this is our first kind of extra law that we can gain. And then we can start observing a couple of extra properties. Like if I were to select the position of the third one and then count how many there were up to that position, there would have to be exactly that many things. So if I were to select alpha and then ask for the rank, this would be exactly the number that I fit it. On the other hand, if what I did was count how many ones there are up to a given position, say this position, and said, oh, there are 1, 2, 3, 4, 5, and then ask for the position of the fifth one, that might be less than or equal to where I started. So now what we have is we have this So for right now, I'm going to start assuming alpha, and I'm going to start assuming S. So these will just become rank and select as single one-argument functions. Unless it matters, and then we're going to be very careful about putting the alphas in. So now what we have is we have rank and we have select, and they have this funny relationship to each other. And if we, yes, it absolutely should be less than or equal to. Thank you. So what we're going to find is if we squinted at this right, we have integers with, 0 is less than or equal to 1, 1 is less than or equal to 2, 1 less than or equal to 3, etc. And what I want to do is view this as a category where each one of these is an object and the less than or equal to is an arrow. Now the less than or equal to relationship composes. So integers with less than or equal to form a category. 0 is less than or equal to 2, 2 is less than or equal to 3. Those two facts compose to get you the observation that 0 is less than or equal to 3. And there is an adjunction between these two, between this category and itself, that says that select is left adjoint to rank. So what the hell does that mean? So let's go through and build this fact up and maybe talk a little bit about adjunctions, and then we'll come back. So I'm interested in trying to unpack this little bit of mathematical notation to those of you who are not familiar with adjunctions. So maybe what I should do is put up another little straw poll. Yes, categories do need identity arrows, but 0 is less than or equal to 0, 1 is less than or equal to 1, etc. So I've dumped the link into the chat. And so far, we're getting a whole lot of what the hell's an adjunction. And a few brave souls who are willing to say that they know what they are. So in order to talk about adjunctions, I'm actually going to switch to a little coding window for just a little bit, just because it's a little bit easier to read, I think, than my handwriting and the stuff going in and out of focus. So statologist, the idea of being able to draw the diagrams but having no intuition, that's what I'm going to try and attack. So I'm going to try and attack a little bit of the people don't have intuitions for adjunctions today, and then see if we can build up the notion that select is left adjoint to rank as an example of an adjunction that doesn't give rise to a monad in Haskell, etc. So we'll find some interesting bits and pieces here, I hope. And maybe some ties to statistics and some other things. All right, so let's flip over to... All right, so about 2/3 not familiar with adjunctions. I'm going to drop the drawing window for a minute and just pull up adjunctions. This thing big enough. Let me slide it over a little bit so that Alex Mason doesn't complain at me. All right, that should be large enough, I hope. Okay. So we know one adjunction in Haskell. So what is an adjunction? So if I say that F is left adjoint to G, F and G are both functors between categories. So I'm going to kind of assume that we have the general idea of a functor. But for those of you who are coming in completely cold, I'll just sketch. So a category has objects with arrows between them, with identity arrows for every object, and the notion of composition of arrows. So I might have, I don't know, integers with, integers is one object here, and booleans is another object here. And I might have the even arrow or the odd arrow. And I might have not. And the composition of even with not gives you odd. And odd with not gives you even, etc. But if I, then were to come from here and give you the constant unit function or something like that, all of my arrows compose as long as they match head and tail. That's the idea of a category. A functor is a mapping between categories that takes objects to objects, arrows to arrows, and keeps everything that's connected over here kind of connected when it maps over into the target space. If that's your level of functors, this is going to be a very not so great experience being introduced to them, so I apologize. All right, so we've got coding and drawing. I'll leave that over off to the side here. So when I say that f and g are going to be two functors, I have like I just want to say like f is a functor from c to d, and g is a functor from d to c. So c and d are going to be two different categories, and these are two functors, one functor mapping down and one functor mapping back that obey a couple of extra conditions. And the conditions that they're going to be able to convey is that arrows from FA to B are going to be in one-to-one correspondence with arrows from A to G of B. So I like to just draw these things right above each other because it makes it easier for me to visualize. This line here is not the turnstile, like the line for the Gensen calculus or anything. It's just me saying, hey, look, everything above this line is in one-to-one correspondence with the stuff below this line. Mainly because it just makes it easy to see. So F is on the left, G is on the right. F is left adjoint to G is the way this relationship works. Now, what is this? This arrow is an arrow in D, and this arrow is an arrow in C. Because F takes, right here, A is an object in C, B is an object in D. F takes objects in C and gives me an object in D. So this notation gets pretty unwieldy once you start having to put symbols on your arrows. So, like, mathematicians tend to talk about these things as, like, Hom sets in, like, D. But this also gets pretty unwieldy. So, in general, I'm just going to draw these things with normal arrows and drop the notation. If I need to be super anal retentive, I'm going to start saying this. So what is Hom? This is like the set of arrows. This is the set of arrows in D from F of A to B. And this is the set of arrows in C from A to G of B. So this is establishing an isomorphism between the Hom sets that we have here. So we know some examples of adjunctions. The one that is probably nearest and dearest to Haskell's hearts is this one. I'm going to make up a bit of a notation here. So by this, what I mean is this. If you were to take A comma E and get an arrow to B, this is in one-to-one correspondence with things of this form. Now, we would usually not write this bottom this way. We would write it as A arrow, E arrow, B. And so you'd see something like this. A comma B, or A comma E, arrow B, is in one-to-one correspondence with this. So what is this? Well, if we wanted to go down, we would use currying. If we wanted to go up, we would uncurry. And given the fact that curry.uncurry is the identity and uncurry.curry is the identity, this is ignoring the fact that there's an extra bottom hidden in this pair, then these two things form an isomorphism that every one of these arrows corresponds uniquely with an arrow down here and vice versa. Okay, so this is the first example of an adjunction that most people encounter in Haskell. And then given any adjunction, so whenever I know that F is left adjoint to G, there's a couple of facts I can observe about this. The composition GF is a monad. And the composition FG is a comonad. So what does that mean here? So let's stick these things together. If I were to stick the two halves of this adjunction together. So adjunctions are a statement about the an isomorphism of certain like hom sets. The space of all arrows from, given for any choice of A and B, the space of arrows from f of A to B is in one-to-one correspondence with the space of arrows from A to G of B. So adjunctions are all about talking about this isomorphism. So the idea here that like GF forms a monad, if we look at this one, we can say, well, what is this? This is E arrow A comma E. In this case, is arrow left adjoint to comma E? No, it is not. You can try and derive that yourself, but let's build it. So we can prove that this relationship is not symmetrical by trying to say, well, if I have A arrow B, or E arrow A to B, is there anything I can put on over here? And I would argue no. There is no way to fill in the question mark, question mark, question mark, question mark. So in the category of Haskell data types, there is no right adjoint to this little exponentiation operator. And we can find all sorts of crazy examples if we move into more interesting categories. I am particularly interested in a very simple category today, which is this select rank thing, where we're just working with orderings, just to get an example of a monad that is not a Haskell monad. But just to kind of see one, if we were to compose these two things in the correct order, G then F, then this would become the state monad. If I compose them in the other order, we get the star comonad. So in this case, both C and D were like chosen to be the category of Haskell data types, But we could go somewhere else. Like given any category, there's an opposite category where we can turn all the arrows around. So what I could do is I could build an adjunction from Hask to Hask op. And I got to be very careful here to get this right. So I want arrows that return something in E are left adjoint to arrows that return something in E. But one of these is going to be in Hask op. So let's see if we can get it right. So I'm going to denote arrows in Hask op as arrows going this way. So A returning E from B, A to B arrow E. Okay. So denoting these as F and G here. F is an arrow from Hask to Hask op, and G is an arrow from Hask op to Hask. Let's scroll this down a little bit more. So now what we have is arrows in Hask op from E to the A to B are actually arrows in Hask from B to A arrow E. These things are in one-to-one correspondence. So I've got this is in one-to-one correspondence with this, but these things are just the same as these arrows. And so if we try and go back and forth from this to this is just flip. If F is left adjoint to G and G is left adjoint to F, then FG would be both a monad and a comonad. Yes, and there are plenty of examples of this. one of the easiest ones to look at is just look at identity. And adjoints have all sorts of nice relationships. They're sort of, if F is left adjoint to G, then, or G is right adjoint to F, each one of them is kind of like the closest you could get to an inverse as possible. And if an inverse exists, then the adjoint will be the inverse. But we can like play around with like identity of A as identity is left adjoint to identity. Why? Because identity of A is in one-to-one correspondence with functions from A to identity B. But this isn't a terribly exciting example because it's isomorphic to one we've already done. But here we have a particular example where, because functions from unit to B are in one, or should be in one-to-one correspondence with B, then we can like continue this chain as many times as we want. So there are very long chains of adjunctions that are not trivial. You usually have to move into other categories. Haskell doesn't have any really long, interesting chains. It really only has, other than this identity one. It doesn't have any long, interesting chains. It has the identity one over and over again. So one thing that's kind of nice about adjunctions is that the left or the right adjoint to a thing is unique up to isomorphism. Like you could come up with a different pair type that you want to have be left adjoint to functions, but it's going to be isomorphic to the pair that we have. You can come up with a few other things. So when I was doing this example, where I was starting to play around with like functions that return an E are left adjoint to functions that return an E. What is that? Well, we say that there's a monad and a comonad associated with that. So what's the monad? So GF here is going to be, well, F is going to take something in Haskell. We're going to go through Haskell op, and then we're going to come back out and pop back out into Haskell. So GF of A is going to look like something like this. A goes to E, goes to E. This is the cont E monad. And FG of A is going to be A goes to E, goes to E. And this is also cont E. Sort of. It's the opposite of cont E. It's a comonad in Haskell op, and therefore it's a monad in Haskell. So cont is its own grandpa. It's like its own left edge. Like if you look at what is the comonad you get from composing the thing that gives you cont the other way around, you get cont exactly. Whereas if you look at state and you look at the comonad you get from composing the adjunction that gave it to you, the other way around, you get store, and it's like actually observably different. That's why there's no like co-cont comonad in the comonads package that I have. It's because co-cont is cont. So we've at least played around with this and started to get some intuition for this. Yeah, if cont is the mother of all monads, well, in a strict language, then, you know, I guess it's its own grandma, at least. Okay, so we have a handful of adjunctions that we've seen now. So let's go back and play with this rank and select thing. So I said before that, like, if I have an adjunction, I have something that is like as close as I could possibly get to an inverse. Like, and if we look at select and rank from earlier, they're really close to inverses. Like, I have, like, rank undoes select. So rank is like a left inverse to select. But coming this way, it doesn't quite work out. So when I'm making this statement that select is left adjoint to rank, what does that unpack to? So we have this original thing. So let's unpack the idea that select is left adjoint to rank. What that means is that if I have that select, I'm just going to write I. Remember, I'm going to let S and alpha be implicit whenever it's not stated. And remember, my arrows here are going to be the less than or equal to thing. So say if select I is less than or equal to J, then I is less than or equal to rank J. And if we were to then choose I to be rank J, we would get the original statement that we made about the inequality. The equality here is actually kind of funny. The equality is actually a stronger statement than you get from having this be an adjunction. And it's because this is a Galois connection. It's a adjunction between two partial orders that you get this extra stronger equality condition on the other side. So you've got this very special adjunction where it's it's a normal adjunction like we've come to expect, but it also has this like super strong property that says that if I were to compose it the other way, what is this? This is GF. The monad here is idempotent. It doesn't actually change anything. The monad here is particularly well behaved. So we have select is left adjoint to rank, and so this is a property that I use over and over again as we move into some more advanced uses for succinct data structures. In particular, I will use it in order to reduce the number of selects and ranks I have to compute. So I'm a big fan of this little bit of math. I don't know that I found it. I haven't found this anywhere in the standard literature. And if you're really wanting to have some fun, you can look around, and there is a co-select that is right adjoint to rank that can be computed just from select. So if you want a fun exercise, I will leave it to the folks here on the stream to go through and find co-select later on. Okay, so that would be something where rank I is less than or equal to J would imply that I is less than or equal to co-select of J. So this would be kind of like what Nadam was looking for on the right of the arrow. There should be something over here. In this case, there is. Or we would like there to be something over there. Okay. So what do we have? We now have rank and select. Let's use them to do something cooler than selecting on like a binary alphabet. Let's like amplify this ability to work with like binary terms to work with a larger alphabet like strings or something. And then compute rank and select on that. See some properties about those orderings. We're going to invent something called a wavelet tree along the way. And there's a lot of uses for this stuff for like compressed text search. I used it for a bunch of stuff for building compressed data storage and stuff like that as well. So we'll see if we can get the general idea of this. Play around with compressed trees, which can be stored in kind of almost optimal space and still be navigated. And yeah, I think that will get to a pretty good point. And then maybe we can play around with a thing that I want to have exist that doesn't yet exist in the Haskell ecosystem. Okay. So what do we say we're going to do first? We're going to try and amplify this to handle like larger alphabets than just zeros and ones. So now let's say I wanted to compute something like, say I have a string FF CD C F A B C D. Throw another F on that, and so let's say I wanted to be able to compute things like compute the rank of C's in this string up to the 7th position. Yeah. So the 7th position is here. So that should tell me 2. But I want to be able to figure out a way to compute it efficiently. And since the only thing I know how to store is rank and select for binary alphabets, I need to build this out of rank and select on binary strings. So one thing that we might try and do is just give me some prefix-free code that has these symbols at the leaves. And I'm going to choose to make this an order-preserving prefix-free code. But like to build out prefix-free code here, you could use Huffman coding. You could use anything you want. I don't care as long as no code is a prefix of another code. Okay? And then what I could do is, given this tree, like I could encode left as 0 and right as 1. And we could say, well, what is F here? F is 1, 1. F is 1, 1. C is 1, 0, 0. 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. And if I wrote this bit string down and then tried to put rank and select on it, it would be completely useless because these symbols don't self-start. They're all variable length. They could be 2 symbols or 3 symbols long. Who knows? Like if I jumped into this bit string at this position, it wouldn't be immediately obvious to me that that is the first bit of an A. These things don't self-start in any meaningful way. But this is the right amount of entropy. This is the amount of information that is in this bit string. Just like if I were to... It turns out like if I pick any balancing of this tree, the size, the amount of information that I have here doesn't really change. My little o terms in my storage adjust. But what I want to do here is say, well, like there's 4 different kinds of decisions being made. Like each one of those bits could represent, did I go left or right at this point? Well, so let's just say, like, what side of the tree our symbol is on. Is it on the right or the left? Well, F, F, C, D, C, F, A, B, C, D, F. Is just telling me which side of the tree I'm on. It's like a bit index in the old Sybase world. The difference is that if we move down to the next level of the bit index, this is now like a conditional bit index, because it's only the things that went left that I'm actually going to bother to encode which side of the tree they're on. Like here, it's only the things that went down here, like that are A's or B's, that we will look at. So what I've done so far is I've written down like these bits. But I'm interested in capturing these bits next. They're the things that were like predicated on the first thing being a 0. What were the next symbols? Well, this A and this B had a 0, then a 1. Okay, and then predicated on the first symbol being a 1, what's the next symbol? Well, FF, CDC, F, skip the A and the B because those didn't start with a 1. CD, F. And then we come down here and we say, out of the things that are C's and D's, which are they? We can say, well, C is a 0, D is a 1, C, CD, 0, 1. So now what I'm interested in doing is computing rank of C's up to the 7th position. And the idea here is if we look at C, it's encoded as 1, 0, 0. Right? We go right and then left twice to get to C. So if I like name these strings, if I just started trying to work my way down, what I could do is this. I could say, well, how many things could possibly be a C at the top of this tree? Well, there are only things that start with 1s, because C is 1, 0, 0. So let's first compute the rank of 1s in this string up to the 7th position. It'll tell me 6. There's 6 things that could possibly be a C. this thing is either an A or a B. I don't really care which. It's not a C. And then we come down here with the 6 things that could be C's. How many of those could be C's with the information I've gained here? So the next symbol I'm looking for is a 0. I'm going to assume this is a rank zeros in this string up to position 6. And it says there are 3 of them. We come down here. We say rank of zeros in this thing up to position 3. How many things are in up to position 3 are there that could be C's? There's 2 of them. So this is the 2 that we were looking for. So we built rank out of doing a chain of ranks. And we had to do 1 rank per level in the tree. So this is sort of time proportional with the code length. So if you have sigma many symbols, you could always build an alphabet that had like log sigma access time. But we've built like just prefix sums, counting how many occurrences there are of a given symbol up to a given position in log symbol length decoding time. This is a little bit naive. There are schemes that try and build slightly larger alphabets than 0 or 1. It works out. This technically works out a little bit better if you have like the log of the if you use slightly larger alphabets than I'm using here. But this is good enough I think for our purposes. So now if I wanted to find the position of the second occurrence of C, what I could do is I could start at the bottom and select the position of the second 0. Because remember, we're going to start it here. And it'll tell me it's the third symbol in this position. Select the position of the third 0. That'll tell me it's the 5th thing. Come up here, select the position of the 5th one. It tells me it's the 5th thing. So the second C occurred there. So at any point in time, if I want to know the position of the first occurrence, I can go select 1. Tells me 3, 3, 1, 3, done. We can find the occurrences in the order they occurred inside the data structure. So this is a data structure that represents a stable sort of information from whatever order I put it in originally to in order by the leaves here, because I could read out the sorted answer. There is 1A, 1B, 3 C's, 2 D's, and 1, 2, 3, 4 F's, and those could all be read directly off of the structure. So I could read this out as, sorted. This would be A, B, C, 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 D, D, 1, 2, 3, 4 F's. This is the sorted version of this string, sorted by the order in which I put the leaves. This is one of the reasons why I chose an order-preserving compression scheme, or an order-preserving code. So there's and yes, I'm basically building up the idea of what wavelet trees are. So this data structure is something called a wavelet tree. And unfortunately, it's named by analogy. There are no wavelets in this wavelet tree. So you'll find some various vocabulary on wavelet trees, wavelet matrices. They're all generally of the same form. It's whether or not you kind of require this tree to be balanced. If you look at a lot of the standard literature, a lot of them require it to be balanced and then make certain judgments about that. I am choosing not to. I prefer to have the tree be pretty freeform. This notion of using rank to walk down the tree and select to walk up the tree is a very general tool. And it goes beyond wavelet trees. It's kind of the workhorse of working with succinct data structures. Okay. So now we have this notion of a wavelet tree. We've got the ability to work on larger alphabets. What other things could we do that use succinct data structures? I think one of the more clever applications of this is to start just playing around with just binary trees. So binary trees are going to actually turn out to suck as succinct structures. They're going to make a pretty good compact structure. But we're going to start by playing with an implicit structure to see where we might get there. So that's one of the reasons why I set up all 3 of those pieces of vocabulary to begin with. So there is one data structure that most people get exposed to in their computer science education at some point fairly early on, which is the idea of an implicit heap. And so what you will often learn is you can store a heap as an array. And we're going to start with our array indices starting at 1. And you kind of point to your children by multiplying by 2, or you multiply by 2 and add 1. So the children of 2 will be 4 and 5. Children of 3 will be 6 and 7. Children of 4 will be 8 and 9, etc. So what we've done is we've unraveled a tree. So if you had a tree that was a complete tree that was only ever missing things on the right, and you're going to build it up in this order, you can always view this as a completely packed array. So you navigate down by multiplying, x times 2, x times 2 plus 1, and you multiply up by dividing by 2. This is a binary heap. Yes, this is a complete binary heap. It's a fairly, this is the idea of an implicit heap. And you can view this as the heap structure. Storing the tree that has n elements takes the optimal amount of space to store those n elements plus a O1 term for storing the size of the heap. This is one of the reasons why this is implicit. If you recall, way, way, way long ago, we talked about some terms. We said implicit is we take optimal space plus a O1 term. Succinct was that we took optimal space plus this funny little o term that said, as our data structure gets bigger and bigger, this term basically vanishes proportionally. And then compact said, we can just, it's optimal space, or it's big O of optimal space. We just kind of threw everything to the wind. So rather than try and build this super fancy succinct index dictionary, we can just try and build a compact one. Just something that is, it's right-ish. That works well enough. And so the scheme that I usually use for something like that is something called Poppy. There is a, let me see if I can find the paper here. Here it is. So this is the paper that I use in practice. It's not succinct, technically. I'll dump the link in the chat. But it's if you had to store your original bit vector for various reasons, then what you're going to do is you're going to pay an extra 3% space in order to get rank and a reasonably efficient select. And I think paying an extra 3% isn't that bad. And I have versions of this in, well, let me pull this back over to the coding and drawing view. So I have versions of this in C++, well, actually in GLSL. I have the versions of this in Haskell. Let's go into shaders and see this implemented in Shaderland. So this is a pile of GLSL, OpenGL shader language that implements Poppy given an index, stored as texture. So you give me the raw data, store it as a bit vector, and then you give me the index for Poppy, and it does all sorts of crazy math in order to do the lookups in constant time. So I'll dump the link to that in chat. So one of the reasons why I like to use this in shaders, again, just kind of speak to applications, is there's a common trick used in graphics where people compute something they call a histopyramid. Usually, like, let's say that you wanted to render an image, and you were ray tracing or something like that, and you did, like, temporal reprojections. Let's say what you said is, here's my frame from here's my previous frame, and I know the motion that the camera has taken. Why don't I go look at that position, or where that position used to be in the previous frame, and if I find what I kind of expect there, let me use its color to try and partially update my current color. This is a common trick in graphics. The problem is like, as you move the camera, like, you'll start seeing, like, stuff that wasn't in frame before. You'll see, like, oh, look, you're now seeing off the desk, or something like that. Or, you know, just behind the couch. The areas that, like, you weren't seeing before. And that stuff won't have any new color information. It's going to look kind of blocky. So what you usually want to do is try and fix it up somehow. And so one way that you might do that is to compute a mask of all the pixels that, like, were not in frame before. So give me a bunch of, give me like this region. And then maybe do more work drawing those things well. So like if I was ray tracing, what I could do is I could maybe ray trace an extra 16 rays or something like that. So there was a, let me flip over just straight to code here. Direct to video. No. Direct to video Matt Swoboda. There we go. He's got a bunch of lovely articles, which I love, from all the way back in the day. He's an old demo scener. Well, what I want to find is he gave a talk on... Come on. Oh, man. Please tell me his SIGGRAPH talk isn't online, or is online. GDC, Advanced Procedural Rendering with DirectX. All right, gotta love the is there anything? I'm trying to find a nice visual of this. So, anyways, the usual technique here. I'll just skip to kind of summarizing the technique that Smash used. Smash is this is Matt Swoboda. He has been around in the demo scene since Dirt. Fairlight does really impressive looking demos. Find something that is actually current. Anyways, if you want to see fancy graphics, go watch a demo by Fairlight. So the technique that they use is they compute these things. He uses these things called histopyramids all over his code. Just go back to the drawing screen here. So what the idea here is, I'm going to compute this mask of ones, and then what I'll do is in log n passes, I will compute the next MIP level, like something that's half as wide and half as tall, and then add up all the ones here. How many are there? Oh, there's 3 here in this little tile of things or something like that. And so I'll get a mask that has numbers, and then I'll take half of those numbers, and I'll keep doing it. So in log many passes, I'll get the total number of values, and then in log many passes I can distribute them back down to tell me how many things are there before me in this array, basically. And I had to do 2 log passes to do it, which is really expensive, and I had to store all of these numbers. On the other hand, I can compute a rank and select structure we worked it out, it's like 3.125% extra space. So this thing had to store numbers for all the positions, then store all the MIP levels, which added an extra third, and then smash them all back. So this is like 32 times larger, times 1.1 1 1/3. This thing is huge. It's like a factor of 40 or 50 larger than storing this succinct rank structure that tells me where are all the ones and like which is this the 5th or the 17th one or something like that. So what can be used for that is, well, what I could do is I could say first do all my temporal reprojection, and then for everything that I wasn't able to reproject, let's cast rays separately for each one of those, say 16 rays per pixel. And when I go to cast those rays, what I will do is I'll just assign one sort of worker, one thread per pixel here. I know exactly how many there are, the total number in this array, just ranked for the end of the end position. Make sure there's a worker that has one thing going for every one of those pixels, and then write the answer into the appropriate pixel that I get by selecting my, like, rank tells me which one I am. Select distributes it to that position. So it's a way to like do work sparsely on the GPU very efficiently. And so I have a bunch of stuff on like in shader code for computing these things as a prefix sum optimally as a compute shader, using inclusive and exclusive scans and stuff. And I'm pretty happy with it. So this was just an example of this completely outside of Haskell. This does not have anything to do with Haskell whatsoever. You can use this for graphics applications and stuff where you care a great deal about memory pressure on a GPU. So one of the examples I like to use, I'm going to keep pointing at Smash's stuff because he's brilliant. And so he builds up, I think fairly early on in this series, this notion of a block map where he's doing just like a grid, and then rather than build like an octree for graphics, he builds just a two-layer brick map. He's like got like one grid, and then if the grid cell is occupied, then he puts a finer level grid inside of it. So it's just two levels, and then you can do something called the DDA walk, which is a generalization of Bresenham's algorithm. But he uses this to like let's say I wanted to build this map and just like use it as like a scene structure to like ray trace through. I could splat all my triangles at this top level grid and just compute a mask of is this thing occupied just by setting it if the triangle touches that grid cell. And then so we build our I'm sorry, I'm not showing the visual. So we build this top level grid here, and then if the triangles touch that thing, then what we need to do is break it up into this tighter grid. But we don't have enough storage to hold like the whole like refined grid everywhere. So what we'll do is we'll allocate as many fine-grained grid cells as there are top level cells that have things in them, and then do a second rendering pass that tries to just draw into the fine-grained grid cells for each one of those triangles. So we'll splat into the top level cells and then select the appropriate fine-grained grid cell out of the densely packed array of those. So we'll have the top level array, which all we did was compute a bunch of ones for where there's actual stuff. And then we have the fine-grained array, which is a bunch of array cells. And each one of these things corresponds to one of these places where there was ones. And we'll just use select to find our position in the fine-grained grid. And so using this, you can build this sort of acceleration structure live on the GPU without ever really touching the CPU. So I just wanted to kind of give an example, like this is useful, like if you just care about like crunching large numbers of rays or something on a GPU, not just for fiddling around with, hey, I've got a bunch of random bits in a single bit vector. Okay. But the tree thing, I want to be able to store a tree in more or less optimal space. And I want to be able to do that by saying, give me an arbitrary binary tree, and what I want to do is represent the tree using a scheme that I will steal from, let's see, all right, I should have a couple of tree structures here. This is getting to the point where I will not be able to do this thing live. But basically the idea is to take a binary tree, and instead of having to have this thing be fully packed all the way from the left, I want to allow holes here. I want to be able to say, hey, look, I've got a tree that looks like this. And I want to store this in sort of optimal space. What I'm going to do is sort of walk through this thing level by level. Oh, this line shouldn't have been drawn. And scribble out, is it present or is it absent at every level? And then use a slightly modified version of this, multiply by 2, add 1 scheme, but now tweaked with a rank. So this works out to be like, compute the rank of my parent. So if I'm at a given position, the children of that position will be, compute 2 times the rank of number of ones up to that position, and then shift. And it works out that you can navigate trees. And those trees take 2n plus little o of n bits. So these were Jacobson trees. I'm just, at this point in time, going to skim through for some applications. Just let me represent binary trees. And then there's schemes for representing, like, if I had a tree that has, k children in any given node. Then there's this notion of using something called unary degree sequences, where what I'll do is I'll just count out in binary, saying like like I have 3 children. Here I have 2 children. Here I have 1 child. Here I have 4 children. Here I have no children, no children, no children, no children. 1, 1, 1, 0, 0. 0 children, 0, 0, 0. And there's different ways that I could store these numbers. Like if I were to store them depth first, there's a form of depth first unary degree sequence. If I were to store them level first, there's a level by level order unary degree sequence. There's 2 schemes called defuds and louds for storing these trees that can be navigated in O1 time as succinct data structures. So these take 2n plus little o of n bits to store a tree. So why do I kind of like that? So I like that because, like, if I were to store this with anything made out of pointers, my tree is going to be enormous compared to this scheme. These things are like, I'm storing trees made out of bits. I can still navigate up and down in O1 time. And to me, this is pretty freaking magic. So we've now seen Jacobson trees. So at least we sketched the idea of Jacobson trees being this generalization of the implicit heap. This does binary trees. These do k-array trees. Defuds and louds. There's another scheme for balanced parenthesis trees where instead of storing these things as the number of children written in unary, where every node is represented by the 1 in its parent and the 0 that ends it. So that's why it's 2n bits. Like this node here is determined by this 0 and this 1. These two things together represent this node's position in the tree. This is not materialized paths. This is not. I'm not storing the ancestor info in the nodes. I'm storing in the nodes. I'm telling you how many children I have. It's a bit different than trying to materialize a path. Like we're not storing the like this node ID, this node ID, this node ID. That would be big. So we've basically got 3 schemes so far. There's this Jacobson encoding where we're just sort of trying to store whether or not a node is present or absent in the tree, and then walking through the trees in levels. We've got these defuds and louds encodings, which are either do I store these unary degree sequences in order, like depth first, or by level. And then there's this balanced parenthesis representation, which is a little bit more powerful, but unfortunately can't be built out of the succinct structures that we've built so far. So there's another thing that you need in order to build this one. But this one is really powerful. It can do a little bit more than these 2 encodings. And it has the benefit that you can kind of build it as a streaming calculation. Whereas these are kind of a mess. Okay. Applications of this. So I'm just going to assume that it is possible to represent some kind of zipper that can walk into a tree. With O1 navigation up and down the tree to the kth child, using one of these encodings, defuds, louds, balanced parenthesis, the Jacobson binary encoding. All of this is implemented. I implemented a good chunk of it in my older Succinct library that I don't know if I ever made it to Hackage, but the Haskell Works packages by Junkie and by Alexi Raga, they have all of this stuff packaged up basically. So one of the use cases, which I believe John will be blogging about at some point relatively soon, probably in a much more focused manner than my rambling explanation, is this notion of quote-unquote semi-indexing, which goes back to a paper by Giuseppe Ottaviano. So Ottaviano, I believe, landed at Facebook somewhere and doesn't work on this stuff at all anymore. At least so I've been told by Shaka. But this paper grabbed my attention and didn't let it go. And so I spent a lot of time playing with this at some point. And the Haskell Works folks have turned around and built this into a Haskell library. So the idea here is let's take... let's just go back to our drawing screen. Let's take some random JSON document or something. And if we looked at our JSON document, there's, foo, 1, 2, 3, bar, 12. Let's say that's a JSON document. I could break this down into symbols that are interesting for navigation and symbols that are not. So I could say that this is interesting, 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 this is interesting. But all of this stuff, maybe there's some spaces in here, I don't know. All this other stuff between these things, I don't really care about for navigation. So I could put a rank and select structure on this bit vector. And then using the same technique that we used to build the wavelet tree, what I can say is if it is interesting, I'm going to store a couple of bits worth of information about everything that is interesting. So I'm going to associate with opening curly braces and opening brackets, pairs of opening parens. and closing brackets and closing braces, pairs of closing parens. And with commas, or I should have done this with colons up here, and with commas, I'm going to associate a pair of parentheses facing outward. And so now what we get is we get associated with this thing a document that looks like this. 2 opening parens, so we now have, in this top level set of parentheses, I have 4 children. And then inside of there, I have those. So if I can jump from the first child of this thing, say, well, is this the string I'm looking for some kind of query that I want to make? I can go up, I can skip over this array. Let's say this could be enormous, like 2 gigabytes worth of stuff. I can jump directly to the next child that could possibly be the field that I'm looking for. And I can do that in one time with the navigation tools that are buildable using this stuff. So the idea here is that we store this and this is just a 2-symbol alphabet. This is, we can call these things zeros and ones. We can do all sorts of fun things down here. So the idea here is that you can navigate down using rank, just like we did before, but now we multiply by 2. Just to, because each one of these each one of these ones is now associated with pairs of parens. And we can navigate up with select, just like we did in the wavelet tree. But we can now navigate this system of parentheses using all the extra parenthesis navigation stuff for walking through binary trees. Eric Domain has do coding and drawing. Yeah, there's all sorts of how do you navigate through level order, unary degree sequence, etc. kind of stuff. I'll just paste this document into the chat. Probably notes from. So Eric Domain teaches the Advanced Data Structures class at MIT, and in there he talks about succinct data structures at some point. And there's a bunch of lectures online from CISO. That is not useful. So I will link to a lecture by Eric on the topic. And through MIT OpenCourseWare, you can find a whole bunch more material here. So if you want to drill deeper, he will talk at great length about the level or unary degree sequence, DFUDs, etc. It's one of the reasons why I skipped over it, because that material is available online. How to kind of stitch this stuff together, there's a lot less material on. I've given a couple of talks, but both of them were recorded with terrible audio. But if you're interested in watching videos with terrible audio, there's a talk I gave at Johns Hopkins on the topic, and a talk I gave at Prezi. Unfortunately, both of them had much worse camera work.
Hi.
So I gave a talk at Prezi on a Blackboard, which is going to a presentation company and using somebody else's presentation software seemed ill-advised. Okay, so those are the previous talks I've given on succinct data structures. They're not as well, they won't be as well recorded as this thing is. Oh, I think did I do a full intro at Yao Lambda Jam? I know I mentioned them in a talk on cache oblivious structures at near the tail end. But I may well have talked about them at Lambda Jam. Oh, wow. I gave a talk I forgot. Functionally oblivious and succinct. So this is almost all about cache oblivious data structures, and there's like 2 minutes worth of succinct stuff at the end to try and make one trick go. So there's a something called a they used to be called fractal trees. So they gave 2 versions of this. And the original talk on fractal trees used a funny little index in order to make searching through multiple sorted lists faster. And that thing turns out to be much more efficiently stored succinctly than the way that it's stored in all literature. So that was the one I used in that paper, or in that talk. So it was just a small application of them rather than a talk on them. Okay, so why do I care about this thing for like JSON and stuff like that? It's kind of nice because if I were to store this bit vector, this is really small. Like this bit vector is at like 1 bit for every symbol. This is like 1/8 of the original document size. This bit vector is really small as well. It's a couple of bits per thing. And it's only for the interesting symbols, and not every symbol in your JSON document is interesting. Only these ones. So storing this index is much smaller than storing the original document, and you can still navigate it for a lot of queries. And so the Haskell work stuff kind of push on this semi-indexing scheme, and they believe they have some support for doing XML schema reading the same way. And John has a library for dealing with walking through CSVs, which I believe was going to be the next piece in the blog post series that he gave. And you could now see it. Like, how would you navigate CSVs? Well, let's just take a CSV document. It's got a bunch of commas in it and some new lines. Well, I could just build one succinct index for where the commas are, another one for where the new lines are, and then I can use it should be fairly obvious how to use select and rank in order to navigate to the ith row, jth column, just using a couple of, like, a rank and select on one of those things, on new lines, and then a rank on new lines and a rank and select on commas or something. And if you have to store your original document, you might as well just store this 3% overhead supplemental index. And it's not even 3%, it's 3% of, like, was it comma or new line. So it's, like, if you tweak the Poppy scheme that I mentioned earlier, you can just use the raw text. So there's variations on the schemes. Like, you could use this to find, build a version of, like, text stored in UTF-8 that supported O1 cutting by storing the succinct index on, or not even the compact version of the index on just, is it a UTF-8 tail byte? So we've now seen there's applications to this to storing JSON. One of the reasons why it's kind of nice for JSON or something like that is if you were to parse JSON, it's going to blow up into data structures in memory. And once it's a data structure in memory, it's made out of pointers and big fat things. And so things tend to blow up by, like, at least a factor of 8 when you kind of unpack it into memory. Whereas if I were to take my original JSON document or something like that and build this little succinct index, I'm adding a few percent to my storage costs, and I can still navigate the document rather than fully unpacking it. This is as opposed to, like, a stream processing like SAX style, where I walk in and out of the document parts, and I still have to touch the whole thing. I can build this semi-index once in parallel, blah, 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 and stitch it together. And then use it just by walking the portions of it that are relevant. So I'm kind of interested in this for a lot of applications. Like an example would be something like if you look at GHC builds these Haskell interface files, and then it has to load the whole thing into memory in order to do symbol lookups. And it might typically dereference one or two symbols and types out of the whole Haskell interface file. But it still has to load the whole thing, and so that whole thing becomes a data structure in memory resident inside of GHC. But with some tweaking of this scheme that we've just described for JSON, we could build a version of data.binary where you serialize out the stuff you were going to write out before, but we also build this sort of is it shape or is it data mixture of things. So we could say for binary, let's say I wanted to serialize a pair of values, and this one was another pair of values, and it had 1, 2, high. Right? What I could do is, these are Haskell tuples. I could represent this as a pair. So I've got the system parentheses using the same kind of scheme. And then represent this thing as a pair. And then here, we could choose to represent this as a bunch of const cells or just as literally the bytes of high. And so what I want to do is I want to store inside of here the information that I had. So if I were to serialize this through binary, then I would serialize a 1, I would serialize a 2, and I would serialize the string high. And then the types would guide me to deserialize this correctly. But I want to make it so that if I just forced this portion of it, I only do the work to deserialize this and not everything else here. Let's say this was a gigantic map of keys to values. I want to only pay to decompose the portions that, if I did a little binary search to find the appropriate key, I only want to force that one path into my big data structure. So what we'll do is we have I could build a top level index of is it shape or is it data? Is it a paren or is there an actual byte worth of character? And then so I've got what do I have? Paren. So these are all shape. Shape. Then data for the let's say 1 takes 4 bytes to store. Then paren. 2 takes 4 bytes to store. Paren. Then high takes say 3 bytes because it's null terminated or something stupid. And then And over here we have the parens. For everything that it was a 1. 1, 2, 3, 4. And then over here we have the data. 1, 2, high. And now what we can do is navigating this thing. I can, if I wanted to just force this too, that basically is saying navigate into the second child of the node that I'm at. If I want to, or the first child of the thing I'm in, navigate into the second child of the thing I'm in. Let's navigate this tree structure, and then I know exactly where I am by walking up here using select and walking back down here using rank. And that tells me the position to start decoding 2 at, or this binary thing. Without storing, if I were to try and do a binary with lazy deserialization naively, I would have to store a pile of positions and all this kind of stuff. And those things are going to be really big. Whereas this is a couple of bits for every tree, every node in my tree. And then this is a bit for every symbol and a bit for every node in my tree. So this is 3n plus little of n bits plus an eighth of the overhead or something like that. And that's the amount of overhead you would have to build a data.binary, where what you could do is just mmap in the file and then tie a thunk to the top of it that is the result of decoding it, and then you only pay for the portions of that thing that you look at in memory usage. So one could build a version of data.binary that used this same kind of scheme. So maybe my throat's beginning to run a little bit dry today, so I think I might end this pretty soon. But I think this might be a fun topic for a future stream, would be building that data.binary stuff to build on top of everything we've talked about here. And there's been a whole lot of silence in the chat. So I have no idea how well any of this resonated after we got into like applications. So one of the major use cases that I have for this is to store this data.binary thing and see what we can do with like encoding these representations on disk that are like sort of optimally compressed but still directly usable. The scheme from here, from the semi-indexing paper, works for any LL1 grammar. So you can use this for XML, JSON, most config file formats, etc. You could probably slap it on DOL or something like that. Is there a way to make these things amenable to updates? So yes, there is. So it turns out there are updatable succinct trees. Fully functional. Dynamizing succinct tree representations. I think this might be the right paper. And so the idea is there's a way to build a version. There's a couple of versions of dynamic trees. There's actually one that has an O1 update. This doesn't work so great for Haskell because it's a mutable algorithm. It's like an imperative thing. So the whole thing kind of has to live in some kind of ST thing. But you can build a version of these trees that let you have a finger that you can push around inside the tree where you're allowed to introduce parenthesis pairs, for instance. And that can be updated in O1 time. So there's a fingered version of an updatable binary, of a succinct binary tree that's navigable. There's a fairly obvious way to build a rank and select structure that can be updated in log time, that can be purely functional, but it kind of loses some of the beauty. And yes, you could use that to avoid reparsing the source file. One of the major use cases that I have for this stuff is, like if I were to do a really fancy C preprocessor, I could find all of the C preprocessing directives and say, well, if you've got an if-def, an elif or whatever, an endif, or a define, each one of these, just using a few examples, could be associated with parentheses in the same way. Like I could say, these are two opening parens. This is a closing opening paren pair. This is two parens facing this way. And this one's actually a new kind of concept where now we have it's self-delimiting. And so you could do this to navigate. You could pre-parse your C source file or something like that to find all the C preprocessing directives, and then walk that skeleton, because between these directives, the set of things that are being defined isn't changing, and then we can parse each one of the chunks between those parens independently using the set of defines that are in scope at that point. And so it's a way to help parallelize C preprocessing. The preprocess is valid regardless of source file, and then this subsequent step. So you can do that as a preprocess, build this little succinct index, and then go. And then if you really wanted to, you could make this whole thing dynamic using one of these kind of schemes. Because it's a system, one of them is a system for parentheses, and the other one is a rank select structure sitting on top of it. And I have a nice parallel way to do that scan as well, using SIMD and bit slicing. But that's a whole other talk, I think. This is effectively turned into a half lecture rather than a live coding session, so I apologize for that. But I figured this was at least one way to get this out. So how well does this play with my monadal parsing thing? It plays remarkably well. So if you look at the one of the, like, how to build this thing as a functional data structure, I'm going to lose a log, most likely, for almost everything. And so you could just shove, like, your rank and select counts into a finger tree and compute it. There's actually a bunch of literature in this space for how to do this in full generality. There's Mihai Petrascu, Succincter was the name of the paper. Mihai's papers, by the way, they were all amazing. Mihai passed away a few years ago, but every paper that he's written is just mind-blowingly awesome. So if you ever want to just, like, have your brain expanded for what is the scope of things that can be done in computer science, his papers are just ouch. And in here he builds, like, a version of arithmetic coding that is random access and, like, using all the succinct stuff. It's like wasting 2 bits of redundancy. He can encode single elements, everything. With very efficient time, and it's just nuts. So he builds this, like let's say you have some kind of aggregate query that you want to run. How much entropy is left in the thing that you're representing after you've pulled out this aggregate by subtracting out all of the space of all possible things that could possibly give you that aggregate. It's such a clean paper. And I learned an awful lot about just how to abuse, like, KL divergence and, like, encoding things with the wrong probability distributions, etc. So this paper leads to all sorts of other things. So I think we've hit a pretty good point here. We now know what a succinct data structure is. We've seen some applications. We've seen it for fiddling with JSON. We've talked a little bit about it for XML. We've seen that we can store trees this way. There's a whole pile of stuff that we could build on top of wavelet trees that we haven't really done. I think it would be interesting to go through wavelet trees for full text search. So, like, future directions that we could do for subsequent talks. I'm just going to do this in the coding window rather than doing it here. So what might we try and do? It was really tragic. He was like Eric Domain's student, and it's one of those cases where, like, the student surpassing the master in many ways, and then he passed away incredibly young. So what do we want to do for future directions? Lazy deserializable binary clone. I really want this. Generalizing semi-indexing for LL1 grammars. There should be some kind of, like, parsing combinator library that you could write this way that automatically semi-indexes the data structure and then builds the lazy syntax tree that unpacks it. So that you would build the data structure that represents the whole parse and then come through and finish up. So I want that lazy deserializable binary clone. That's definitely front and center of my thoughts. Fancy C, pre-processing. We talked a little bit about it. We could go deeper into louds and defuds. how to build like structures that are good at aggregate queries. Loads, defuds, balanced parenthesis representations. So updatable versions for appending. So if we look at like the scheme that I gave earlier for when I mentioned Poppy, when you work with Poppy from left to right, you could always continue to append to the Poppy stream, and that's fine. So that gives you an updatable. Like if you just have a bit vector that's continuing to grow to the right, there's all sorts of cool things you can do there. There's like a data.vector like clone that could also live here. But each one of these things relies on a trick. Oh, thank you very much, Negatron, or I can't pronounce your name. I apologize. So there's a really general scheme that I use for dynamizing immutable data structures. So Vibev, you were saying something about like, or was it Vibev who asked the question about whether or not there was a dynamic version of this? Somebody did. Anyways, so whoever asked the question about is there a dynamic version of this? There's a fairly general scheme for dynamizing almost any imperative or any immutable data structure that relies just on monoids. So let's do that. I think that's a good. So I'll just do dynamization. Then we'll come back into how we might apply it to rank and select and building big aggregate data stores. Yeah, let's do dynamization. Okay, so here's the problem. There's a whole bunch of ways to build data structures out of number systems. This is a central topic in Chris Okasaki's book on purely functional data structures. And there's an old dynamization scheme for how to make static data structures dynamic. I'm going to recast it all in terms of monoids because this is the way I like to think about it. And the idea here would be like if you were to take a like counting in binary. We could turn this into a data structure for working with like a linked list, where we've got a linked list of trees of size 1, 2, 4, and 8 right here. So here we have a data structure. We have nothing in the list. Here we have one data structure size 1, one data structure size 2, one data structure size 2, and one data structure size 1, one data structure size 4. And then the idea would be like, in order to put a new element into the list, we would have to const onto this thing somehow, which would have to like create a new element and then merge two data structures to size 1 to build a data structure size 2. So this scheme doesn't work so great with binary, but people have figured out that there are other structures that we could use. Like we could use skew binary and build a notion of a random access list. And skew binary, instead of nodes being... This is like 2 to the k. We could use 2 to the k plus 1 minus 1. So this is going to give me sizes like 1, 3, 7, 15. So it's 1 less than the power of 2. So a skew binary structure, you're going to count with binary digits, except you're also allowed 2. But you're only allowed 2 for the least significant non-zero. This is 0, 1, 2, 3. And one of the benefits of working with skew binary over binary is that carries only ever have to carry 1 digit. So it has a very slow, like if I do carries for incrementing, then carries only work one digit at a time. So we can build, this is the idea of a skew binary random access list. We can build like, so if we look at these things, 1, 3, 7, these are the number of elements in a complete binary tree of a given size. So one node, complete binary tree of size 2. There's 1, 3, 7 things, etc. And so the idea is if we were to store this as a linked list from the least significant digits up towards the more significant digits, I could just build like a binary tree of A's, which holds on to, or either tip or, and tip actually holds on to a value. We have an A and let's call this just a tree. And for my sanity's sake, I'm going to store how many children there are in every node. And then I can build a skew binary random access list out of a list that is either empty or contains like how many things are there in this tree. And I'm way inefficient here. I'm storing way too many counts and stuff. Just trying to get the general idea. We'll bang our way to glory. All right. Skew A, nil, const, tree, skew A. So how will we bolt things into this tree? We would do something like, given an A and a skew A, I'll give you a new skew A. So consting anything onto. The idea here is this. If I were to store, if I had two things of size 3, and I needed to get to the next thing, I would need one structure of size 7. And I can do that by just bolting it on as the root. Otherwise, I will bolt it on as a new tree to the left. So if they're the same size, then we're going to build this as a new const cell of size n plus m plus 1. These are the same thing. Bin n plus m plus 1. The new root, A, A's and B's, C's. Otherwise, const A, A's is going to be const 1 entry. Actually, I can just get that out of the tree. I don't need to store it there. Const 1 thing. There. So we now have a const. And if you work this out, this will start with an empty list of trees. And then it'll build the tree that has 1 value in it, threaded onto the empty list, and then it'll build, like I put my second entry in there, threaded onto the empty list. Then I will build 3, 2, 1, threaded onto the empty list. 4, 5, this gets turned into a tree with 6 in it, and then I put 7 up here at the root. And so we would continue to build complete trees, and we're going to wind up with a threaded list of complete trees where every tree is larger than the last, except for the first one might be the exact same size as the next one. This is the idea of building just a data structure out of a number system. We took the number system of skew binary arithmetic, where our positions were not quite the value of our original binary numbers, and we had this rule that we're allowed to use 0, 1, and 2, but 2 must only be the least significant non-zero. Digit. And that's enough to make these numbers unique. Okay, this is one example of a data structure from a number system. And it's possible then to compute how to do log time indexing into this tree. Because it's like the size of the trees, you can just skip. If I'm looking for indexing the ith member out of a skew binary array. M and N here are the size of these things. I have a Leonardo tree. I'm not going to do it today. So anyways, the whole point of having this log time indexing into, well, I guess I leave it as an exercise to compute the index and the rest of this stuff. So I started with a binary number system. And I could build a data structure that was that represents like, just like binary as a number system with binary A. I don't know. We're gonna smash these things together using some kind of monoid or something like that to do the merge. So we can have like a D0 or a D1 A. And then these start from like the least significant bits and go up. And then I could build like consts if I had a monoid for A to smash this thing in. Given an A and a binary A, I'll give you a binary A. And then some kind of query that acted as a monoid homomorphism, I could pull this out. This one's a mess, so I don't really like this structure. Like these D0s, I'm skipping a thing. There's no structure there of that size. This turns out to not be good enough to fully deamortize all the access to this thing. Like the fact that this is a carry here can cause me to do log n merges, and each one of those merges could be big and expensive. Means that binary is the wrong number system here to build most data structures out of. So there was a scheme that is mentioned in Okasaki's book for zero-less binary, where you can build numbers, like you can build, my digits are still binary numbers, but I'm allowed to have 0, 1, or 2, but only leading zeros. So like we could have 0, 1, and 2 as our binary digits. But now so we're counting in binary, but now we're counting with 1s and 2s. And we can view this as like we've got 0 leading up to this thing. Just we've got like an infinite prefix of zeros. And after you get to the, like, past this sort of warm-up stage, these look a lot like normal binary numbers. The least significant digit is alternating every position. The next most significant digit is alternating every other position. But we got this, like, the 0 worth of warm-up time. This turns out to not be enough. So I have this modified zero-less binary system that I use to build a scheme that I'm pretty happy with. And the idea is you're allowed to have 0, 1, 2, and 3, but only an infinite prefix of zeros. And 1 can only be the most significant digit. So now you get 1, 2. This is the best way to talk in binary I've ever seen. That looks like binary to me, right? I'm still streaming, hon.
Okay, never mind. Thought I heard you.
0, 0, 2, 3, 2, 0, 0, 3, 3, and then we go up to 1, 2, 2. So what's going on here? What do we have? If we look at the least significant digit, after this warm-up period where we start at 0, which could be very long, we then pass through 1, and then we go into this alternating between 2, 3, 2, 3, 2, 3, 2, 3. The next most significant digit has this long warm-up period of zeros. Then it goes through 1, and then it goes through 2, 2, 3, 3, 2, 2, 3, 3. And so we're doing the same slow warm-up as before, but it's even slower. Like we now have this, instead of having to just go from 0 and then go immediately into 1s and 2s. We go through 0s and 1s before we get into 2s. So why did I bother with all of this craziness? In between the time that I have 2 data structures of size 1 and I need 1 data structure of size 2, I have 2 time steps to to finish paying off the merge. Like the problem here was, like, let's say I had just, like, if I were like working with like normal binary, if merges were like linear in the number of elements or like the size of the structure, like if I had a data structure that looked like just was a big pile of 1s, and you gave me a new element, I'm going to have to do all these merges, and these merges are going to be expensive. This is 01. This is one step. This costs me 2. This costs me 4. This costs me 8, and then I'm going to merge all that together to build one data structure of 1, 2, 4, 8. One data structure of size 16. If this was 2 to the 32nd elements or something like that, that becomes much more expensive. I don't want to pay to do all these merges, and I don't want you to be able to time travel back to the time when I had the previous data structure that was in my binary thing, because we're in an immutable world, so I can go back to old versions of the structure and force me to do the same const all over again. So const was linear in the number of elements when we worked with binary in a immutable world. So this is crap. Don't do this. This scheme, the zeroless binary, was not enough, but this scheme turns out to be enough. So in between the time I have 2 data structures of size 1 and need 1 data structure of size 2, I knew what they were that I was going to merge for 2 time steps. So what I could do is I could create like a little layaway box. I could store the thing that I'm going to work with. So I can make d of a is, like, from the point of view of the least significant digits, if the least significant digit is a 0, there's no more significant digit. If the least significant digit is a 1, there's no more significant digits because they're all zeros. I'm going to store these with bangs on them. So my trick here will be to create a place for the merged versions of these, which is unbanged. And d of a to d of a. Right now, we're exploring how to make almost any static data structure dynamic, and I'm using a very generalized scheme that goes back to Overmars and Van Leeuwen from the 80s, and talking about like how to build this in Haskell just using monoids. Why is there no A after the D1? What do you mean here? D1 holds on to a single A. Oh, there's no DA this thing, because the next most significant digit after a 1 must be a 0, because like a 1 can only be the most significant digit we have. And as for why these A's are not strict, this is going to be because I'm going to put a thunk here that will be the result of merging these two things. So basically, if I want to const A onto D0, I'll just get D1. If I want to const A onto D1, I'll get D2. And the next thing is going to be a D0. And what I'll do here is, I've got a monoid, so I'm just going to append these two things. This will be a thunk. I can't afford to do this work. This monoid, I said my monoid could be linear time in the size, like the number of A's I've matched together, or the number of like A's I like if I were to completely expand this out into trees. Const A D2 BC, the BC thunk D. This will be a D3 with an A B C. The BC thunk passed along unmolested. And the remainder. And so what did we do? When we increased from 3, we went to 2, but we bumped the next guy up by 1. So we're going to go, we have a D2. It's got A and B in it. It's got A appended with B. Here the trick is that at this moment, I've done enough work to pay off the CD. Here. So the idea here is what we've done is we've said, okay, I now have 2 elements, and I have the ability to merge elements together. This merge is expensive, so I'm not going to do this merge until you've fed me enough elements to pay off the merge. That will happen 2 time steps later when I finally force it. So we went from 0 to 1, 1 to 2. Now I know the 2 elements I'm going to merge in order to make this array of size 1. And that will happen 2 time steps later after I've paid off the thunk, at which point in time I can afford to force it. Why monoid and not semigroup? That is a good question. I only need semigroup here. The queries I'm going to execute against this thing, you give me a DA and a monoid B and a monoid homomorphism. And I'll give you a B. So, So what do we do to query this thing? Well, you query me with some function against D0. This is just mempty. Query F, D1B, D1A, just F of A. Query F, D2, AB, C's. This is F of A appended with F of B appended with query F, C's. This is morally it's equivalent to saying fold map. This is stronger than fold map. It's fold map with the requirement that you give me a monoid homomorphism. And so the idea here is like the ones that I put the bangs on are actually the elements that we really wanted to store here. The ones that I didn't put bangs on are like layaway accounts that I'm going to afford to pay off in a couple of time steps. So this scheme is a very, very general scheme. For any time you have, it's not a functor. Notice that query did not give me a D of B; it just gave me a B. It's almost like fold. It's almost like fold map. So given like you have empty, we have empty and const. I guess we'd call it nil. We have nil and const, so we can build up bigger and bigger things that we can perform queries against. If you have a way to represent your queries as some kind of monoid homomorphism, then what we can do is this. So what do we want? We have some kind of monoid. We have some kind of structure that we know how to build, that we know how to smash together to build a bigger structure. And we have some kind of query that we know to ask to get a result. And I can smash these together with a completely different monoid and get the answer for the result of having queried the composite. As long as you have this kind of shape where I can query this thing and then query this thing and then glue the results together of the queries, or I can glue the structures together and then query the result structure, then this is the kind of thing that this D thing that I just sketched here, this generic dynamization scheme, can be used to improve. So let's use it. One of my favorite use cases for this is to use, like if I had sorted arrays of keys, and this operation was merge, and this query was is it present, and then this monoid was first, like the data.monoid first, then this becomes build up a bunch of sorted arrays and then merge them. But then I'm doing queries against like roughly 2 log n sorted arrays. So this is log squared n to query. But because the arrays have such coherent memory access, if I can do this with like packed arrays or something like that, this actually turns out to be more efficient than using data.map. As long as you have a map that you only ever need to be able to insert into. What's that? Just insert like const single element arrays here, up to about 1 billion entries, than a normal data.map. It's within a factor of 2 to query. Like it's a little bit slower to query, but it's about a factor of 7 faster to build. So if you have like a insert often but query infrequently map, like let's say you have like a symbol table, this is a way to build a very efficient symbol table as an example. And maybe what you do is you, like if you have, like if the constant factors are bad here, what you do is you put a normal map on the front of it, and then you take the entries of that thing and you just dump them in mass. So you can build maps and sets and things like that out of this structure. But I could also do this for rank and select. I could say I have some kind of data store that holds a bunch of things that I'm interested in querying, and I have rank and select for more data. Like you give me more and more rows worth of data, and as long as I have a way to glue these things together using some kind of monoid, and I have some kind of query that I know how to stick together, I can pull this together. The scheme that I gave here used a monoid. The monoid is not necessarily the right construction. Maybe I know something like the size of this, and I'm going to glue it together with the size of this. Previously, we've talked about like semi-direct products. So like you can come up with a version of this that works with a monoid acting on another monoid, like with a semi-direct product, and this query has that same kind of structure. And it turns out to be kind of necessary later on in order to talk about this thing for ranks in its full generality. But there's lots of things where, like, if I wanted to compute rank on something like this, where I had a structure here that I knew how to compute rank on, and a structure here I knew how to compute rank on, what I could do is I could build just a little tree, and that tree would have like roughly 2 to 3 log n leaves, and so it's going to have log n height, So it's going to be like at most height 5 or something like that in practice for something enormous. And I could store just the prefix sums up to a given position of my ranks and do rank queries in log n against this aggregate grown thing. This is just an example of like how you might apply this scheme to rank and select. So this bit here, this dynamization scheme is fully general. I like it that it fits kind of nicely on a screen. As sort of an example of let's use a monad homomorphism for good. So there was an old paper by Overmars and Van Leeuwen that talked about this scheme. From 1981 or 1983. It's used for convex dynamization. Two general methods for dynamizing decomposable search problems. And this was phrased in very imperative terms. But if we tweak it, we get this number system kind of presentation, and we can think about everything in terms of monoids and whatnot. There was a cute little paper let me just add Overmars or something like that to this list. No, this isn't the one. This is I was just looking for a short little lecture on dynamization. This isn't it. So I haven't given the how to improve this in the presence of like weak deletes. Like if this assumed that I only ever inserted into my map and I didn't delete from my map. You can build a version of this that has this delete by giving you like a tombstone, like you give maybe A's or something like that as the values, and then as they merge, they crush out the old things. This leaks a little bit more than a map. Like you hold on to all the stuff until like it's fully been forced out of everything until enough merges have happened. So it leaks a little more memory than a map as you've come to know it. Its queries a log time slower. So it's not a panacea by any means, but it's kind of interesting that just playing with these like data structures from member systems work. So the next problem is of course this like notion of like soft deletes. The asymptotic cost of querying is now like log squared n in the total number of elements that have ever been inserted, not the number of live elements. Like deleted elements, we're building up these tombstones, and so there's a whole other layer of dynamization you have to do to like incrementally build the version without the tombstones, so that once you reach like 50% tombstone occupancy or something like that, then you switch to the new one, and then you get correct asymptotics for all the operations. But the Overmars and Van Leeuwen paper that I linked is probably the right direction if you're just curious. So this is like from 1981, 1983, somewhere in that ballpark. God damn it, where did that paper go? There was a cute little paper that did a nice introduction on this, which made it possible for me to see this. So I used this in that Cache Oblivious Succinct. Cache Oblivious and Succinct data structures talk that I have mentioned earlier. So why do I care about this for succinct data structures? Let's say I had like a data store where you're going to give me lots of rows worth of data, and you're interested in doing like aggregate queries, like give me total sales in 2012 and stuff like that. I have some fancy things where I build little wavelet trees to represent the rows of data that I want to have, and then I have like other rank and select structures that I'm using to do things like compute sums over row ranges and stuff. All right. We've run about a half an hour longer than I said. I should probably wrap here. So let's go back to our future list. We've covered dynamization, sort of. Updatable versions for appending. Well, we could do the same scheme. Like, let's say that we were just, like, not even sorted lists of arrays. We'll just do arrays with concatenation. Then what I could do is build like a version that worked like data.vector, where let's say I wanted to deal with like a form of data.vector that could deal with sum types, but could also give you log time indexing into the array. But like log time and still quite efficient, or log time indexing into the array. What I could do is I could store that same scheme, give me prefix sums of, what did we say before? We said we'd store like the number of children to the left of me, or to the right of me, and my leaves are like just flat arrays with elements. So we've got a complete binary tree with elements are arrays that are getting smaller and smaller and smaller as we get, or I guess they're constants, so they're getting smaller and smaller and smaller on this end, and bigger and bigger and bigger on this end. And we're going to continue merging arrays of the smallest size gradually as you insert more elements, as you go to const more elements onto the front of my array. But I want to give you log time access, and I still want to be able to support things like sum types and product types and store this thing densely. So how would I store like a sum type? Well, I could store it either as a bit vector that tells me 0 or 1, are you a left or a right? And then over here I could have, here's a structure that has, for everything that went left, here's a structure that I can efficiently query. And everything on the right is, for everything that went right, here's a structure I can efficiently query. So we could start to say, give me like packed arrays, as long as I know how to like const onto this thing and query into it in log-ish time. With an O1 const or an O log n const. Log n const. To get like a data.vector style, like split out my products, but also split out my sums by splitting out my sums by using this little succinct bit index to tell me whether or not something was left or right. And then use, well, looking at this element, it'll tell me it's a 1. And there are 1, 2, 3, 4, 5, 6, 7. That's the 7th 1. So I've taken all the error out of it. I don't have to store both the left and the right-hand branches or something like that. So data.vector can only handle product types. This can handle sum types. So you could build a version of data.vector that supports sum types. Updatable versions of this for appending. We've kind of talked about dynamization, at least, for that. Aggregate queries can be done with rank and select, and then like putting rank on, like, let's say you wanted to do sums, you could put rank on your 1's place, rank on your 2's place, rank on your 4's place, and then do range queries on rows and stuff. But I think we've hit kind of information saturation about a half an hour ago. So I'm actually looking at adjusting the stream time a little bit. The Wednesday talk seemed a little bit late for folks, and this is seeming a little bit early for me. So I was wondering what folks thought about sliding the talk, or the streaming sessions maybe back a couple of hours on Sunday. Yeah. And what people think about sliding the Monday or the Wednesday slot that I started trying to do this week a couple of hours earlier. So my druthers would be to slide this slot like 2 hours, maybe 3 hours back. I mean, it's the middle of summer, and this is the height of the day, and I'm under all these lights. So right now it's... I realize this is slightly biased by the fact that people are here right now at 2:30, so... And yeah, I probably would overlap a bit with Brian. I might coordinate with him to see if he would like to slide a little bit back. If we did 2 p.m., then it would be like if I did a 2-hour stream, then I would dovetail perfectly with Brian. And yeah, we did kind of have a thing going where I would try and hand off to him. I haven't been running 4-hour streams for a little while, though. So it hasn't been working so well to try and do the 4 p.m. Or the noon to 4. I just find I run out of steam about 2 hours in now. What are the results on this one? So regardless of what we do on Wednesday, I probably will not be streaming this week. John Wigley will be in town, staying with me like from Monday through Wednesday. So I would be a terrible host. I don't know. Maybe I could get him to join me on the stream. It'd be kind of cool. But so I think I'm going to skip Wednesday this week. Do I have purple lights or is that hair dye? It's probably the color adjustment to make me not look orange. I have very bright lights around me, but they're all white. Head. Let me tweak my filters. I am wearing a slightly purplish shirt, though. Yeah, so like if I go to true, I look purple as whoa. So, I guess I'd rather be an Oompa Loompa. And meh. It would be fun to have John on the show. I'll have to talk to him. I don't know if the timing works out because I know he's working until 5 p.m. that day or something like that. And I don't really want to ambush him right as he gets out of work. So I think what I'll do is I'm going to move the Sunday stream, I think, to 2 p.m. This coming stream, and then I'm going to skip Wednesday because John's in town. And if he's super keen on doing something, then maybe we'll arrange something rather ad hoc later on that Wednesday, but I don't want to force it on him. Hi, DeFi. My name's Edward Komet. I do a lot of work in the Haskell ecosystem. Most of what we've been doing here is just, like, sort of deep diving on, like, harder technical problems. Today we did a bunch of stuff like playing with something called succinct data structures, trying to build data structures that are fully compressed but still efficiently usable. In the past, we've covered... oh gosh, what have we covered on the stream? The first time we went through using commutativity, like the fact that you can, like A plus B equals B plus A and stuff like that, in order to build a bunch of efficient data structures in Haskell. Like, started talking about it for doing probabilistic programming. We've done some Q&A stuff. We've done... we built a little library for doing authenticated computation running on a server. We've done, like, playing with inverse semigroups and lots of math. What else have we covered here so far? We've covered a lot of topics on this stream. We built a bunch of stuff for playing with abstract machines for how do you do interpretation for functional programming languages. That was been the last couple of streams. I think that covers most of what we've talked about. Well, Deethai, Mitaman, this shows up in the programming Twitch search. So, oh yeah, we covered that was was in the inverse semigroup thing, inverse and regular semigroups. We found that a quirk of Australian English turned out to be a regular semigroup, but not anything stronger than that, which actually disappointed me a bit. I'm going to need to figure out how to do that for a talk. So let's see. So I think administratively, I think the Sunday will be 2 p.m. and I'm gonna drop Wednesday this week, and we'll just pick up then. And hopefully on the Sunday stream, I'll have a little more to say on like the whole Miri front that I talked about last week, or on Wednesday, just a little bit. All right. Well, I think that's everything that I have for today. I think I'm going to wrap here, and I will see everybody next week. Cool.
You're still here? It's over. Go home. Go.